Hello everyone, I hope you're all doing well. So today we're back looking at the 75 Leetcode questions, and I'm going to try to move through these solutions a little bit faster. Last time we did a string problem, but today I think we're going to tackle a couple of the binary tree problems. So let's just pick the first two. We'll look at the maximum depth of a binary tree, and we'll look at the same tree problem. So let's start with the maximum depth of a binary tree. Before we get into this problem, let's talk a little bit about the binary tree structure itself. So if you're already familiar with binary trees, go ahead and skip the next part of this video until we get back to the solution. But if you're not, stick around and I'll explain a little bit more about the data structure itself. So binary trees are just a well-known data structure used to hold various kinds of data. So here we have a binary tree that holds numbers, but you could think of a binary tree that holds strings or characters or really any kind of data. It could even hold records, which have a lot of different values. Now, before we talk about binary trees, I think we need to get on the same page about some verbiage. So the root node is the topmost node of the tree. So here in this problem, the root node is 1. It's the topmost node of the tree. It has nothing pointing to it, but it has things it points to. Because it's a binary tree, each node has a value, a left pointer, and a right pointer. So here, the value is 1, this is the left pointer, and this is the right pointer. Again, if we move down the tree, on the left-hand side, the value here is 2, the left pointer is 4, and the right pointer is 5. And you can keep going until you traverse the whole tree. Now, when we reach a node that has no left pointer or no right pointer, we call that a leaf node. So in this case, 7 is a leaf node, 5 is a leaf node, 8 is a leaf node, and 9 is a leaf node. 4 is not a leaf node because it has the left pointer. Now, we can also talk about nodes in terms of their relationships to each other. A parent node is a node that comes before a child node, and a child node is the direct descendant of a parent. So in this case, 1 is a parent node, and 2 and 3 are its children because it points to those nodes. Then 2 itself is a child, but it's also a parent because it points to 4 and 5. 4 and 5 are the children of 2. 4 is a parent because it points to 7, but 5 has no children. So we can look at this relationship, parent-child relationships, to talk about how nodes are related to each other. We can also perform various search algorithms on the trees to get the values in different ways. But for these problems that we're going to solve in this video, I think we'll use a depth-first search approach. So what does that mean? That means we're going to start at the root node and explore as far as possible before backtracking. So in a depth-first search, you might start at 1 because that's the root node. Then you would go as far left as you possibly can before you start backtracking. So we would go 1 to 2 to 4 to 7. Then we would start backtracking. Okay, 4 has nothing on the right, so backtrack to 2. 2 has a pointer on the right, so now we're at 5, backtracking until we go down the right-hand side, so on and so forth. This kind of algorithm lends itself really well to recursion, and we'll discuss that further in the solution.
And now back to your regularly scheduled program.
Given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So in this example, the root node is 3. The pointer to the left points to a node that's value is 9. The pointer to the right points to a node whose value is 20, so on and so forth. The maximum depth of this tree in this example is 3. That's because of the longest path, where we increment a counter each time we encounter a node. So let's conceptualize how we think we want this algorithm to run. When we hit the root node, we're automatically going to add 1 to our maximum depth counter. Then we can traverse left, keep traversing left until we've gone the furthest down, count the depth there, then traverse right, keep traversing down, count the depth there, and return the maximum depth that we have. So when I think about this solution, I think this problem lends itself very well to a recursive approach. So that's the approach I'm going to take. If you'd like to see a different approach, go ahead and comment it down below, and I'd be happy to talk through that. Let's go ahead and just sketch out our algorithm. In a recursive kind of approach, we need to have a base case. So our algorithm is going to call a recursive function to do all the work. Then we'll just return the value of the recursive function. Return val of recursive function. So what is our recursive function actually going to look like? Well, I think as input to our recursive function, we're going to need a way to keep track of the maximum depth. So input is going to be max depth, and we're going to need a way to keep track of the current tree. we need to define a base case. So the base case will be when we've hit a node that has no more pointers. So there's no pointer to the left or no pointer to the right. So when we've hit a leaf node, turn the depth. Then the recursive case, we need to actually traverse through the list. So we need to get the maximum depth, get max depth from left and right subtrees. So how about we just say get depth from left and right subtrees, return max. So that's an overview of our algorithm. So let's go ahead and implement this. Now in Python, this self function would allow you to do the recursion right in the body of this function. However, I don't think that that's the cleanest approach or the easiest way to learn. So I'm just going to declare a recursive function right inside the body of this max depth function. So I'll call this function recurse. You could call it depth first search or whatever you want to name it, but I'll call it recurse just so we're on the same page that this is the recursive function. And again, to the recursive function, I'm going to pass a depth parameter, which keeps track of how deep we are within the tree, and then I'm going to pass a tree. So I'll go ahead and just call that tree root. So the first thing we need to do is the base case. So if the root, so if this tree that we passed in is none, meaning that it has no left or no right pointer, then you're going to return the depth. Otherwise, this is where we're going to do this maximum magic. So we're going to return the max. That's the Python function call for maximum. And each time we make a recursive function call, we want to increment the depth counter because we've moved down one more in the depth. So 1 plus, well, we need to recall the recursive function. Recurse 1 plus depth, comma, the root. Now, I'm going to give you a second to think about what parameter we want to pass in as a second parameter because we want to move through the tree. So I'll give you a second to think about that. Now, if you came up with the answer of root.left, you're right. We want to recurse down the leftmost side of the subtree, and then we want to recurse down the rightmost side of the subtree. So we're going to have the maximum value of the left recursive call, and then we're going to have the maximum value of the right recursive call. So 1 plus depth, root dot right. So let's double check our parentheses. Always nervous about the parentheses. So now we need a function to actually call this recursive call inside the max depth function. So we'll go ahead and just say return the call to recurse, starting out with the depth of 0 and the root node or the root list that we've passed it. So what is this algorithm actually doing? So it's entering the recurse function call right here with a depth initially of 0 and the root node. So the first time we go through this call, the root node is 3. So the root node is not done, so we're going to return the maximum of the recursive call to 1 plus the depth. So now the depth is 1, now the depth is 1, and the root node is the 9 subtree. And on this side, we have again, with the depth of 1, but this time it's the rest of the tree. So over here, we have 1 comma rest of tree, right of, so on and so forth until we get to this none case in which we just have the maximum depth. So let's run this and make sure that everything I'm saying is actually true so we can run with our test cases. So I think the parentheses here are just off on the call to the maximum function. So let's redo our parentheses, try it again. And it looks like it was right, so it's just a parentheses issue, so we'll go ahead and submit it. Again, this complexity is big of n, so we beat some users, our memory usage could be better. This is the best solution for learning. So now let's go back to the 75 questions and let's work on the same tree question next. So the same tree question says, given the root of two binary trees P and Q, write a function to check if they are the same or not. Two binary trees are the same if they're structurally identical and the nodes have the same values. So we need to do the same kind of depth first search approach, checking the value this time at each node, making sure that the values are the same, and then if they're the same, we'll proceed through the algorithm. If they're not the same, then we'll automatically return false. So again, I think this problem is best solved with recursion, but if you have any other thoughts, why don't you go ahead and comment them below. So let's go ahead and sketch out the recursive approach to the algorithm. In the recursive call, we need a base case. We're going to have a couple different base cases. So the first base case is going to be if both trees, so in this case if P and Q are both pointing to none, then we know that we've reached the end of the tree traversal and we can go ahead and return true. So base case, both trees will say empty, because we've traversed through the whole thing, so we can return true. The second base case is that we actually have a mismatch. So either maybe the values aren't the same, or one tree is pointing to nothing and another tree is pointing to something. So values not same, or one tree pointing to null. In this case, we'll want to, the trees are not identical, so we'll want to return false. Now we have actually the recursive case. So in the recursive case, we're just going to consider the left and the right subtrees. So now let's actually implement this algorithm. Again, I'm going to make a function call called recurse, which takes in two trees. It's going to take in a P and a Q tree. Here's the first base case. If P is none and Q is none, this is the case where we've traversed all the way down to the tree, or maybe the trees were just empty to begin with. But either way, they're identical, so return true. Now in the case where one tree is maybe empty, or we've reached the end of traversal on that tree, or maybe the other tree is empty, or the values don't match. So this is where we do the p.val does not equal q.val. Then this is the case where we want to return false. Now the actual recursion is very simple. It's just calling recurse again. So we'll call recurse, or we'll return recurse p.left, q.left, comma, recurse. Because this function is expecting a Boolean, we need to return an and statement, not two function calls. So and recurse p.right, q.right. So then outside of this recursive function call, we're going to kickstart the algorithm with recurse and the trees we passed in, p, q. Again, we need a return statement around that. So let's go ahead and run it and see if we got the correct answer. And we passed case 1, 2, and 3. So what is this algorithm doing? In this base case, we're at the end of the tree. So we've gone 1 to 2, we've compared everything, we're good to go. In this case, if the values don't match, this is where we'll return false. So here, 2 and 1 don't match, so we're going to go ahead and return false because of this case. Here, we have something at the left pointer of the root node, but nothing at the left pointer of this root node. So that's why we're returning false here. Otherwise, if we pass the case for the current tree, the current subtree, we're going to return and recurse. So this solution does solve the problems, but let's go ahead and try on all the problems Leetcode has to offer. And we beat 87% of users with Python 3. So both memory and runtime were good. That's because we're only ever doing one comparison per node, because each time we're only looking at one node and comparing the value there. So happy coding, everyone. I hope you enjoyed this video. If you have any other videos that you want me to do, or any other Leetcode questions you might need help solving, just go ahead and leave a comment below. Bye, guys.